Today we're going to talk about exponential functions. So far this year we've been dealing with linear functions, which we know will create a straight line when we graph the function. A function in the form of y equals ab to the xth power is called an exponential function. Exponential functions are not linear. Linear functions have what we call a constant difference, whereas the exponential functions have a constant factor of the values. A is the y-intercept of the graph, and b is the constant factor of the y. So how do we identify whether a function is linear or exponential? Well, one way to do it is to look at the table of values that we have here for a, b, c, and d to determine how are the y values or our outputs or our ranges changing. Obviously, when we talked about linear functions, we talked about having that constant rate of change or the slope. So in table A, we can see that the x values are all increasing by 1. And at the same time, we can all see that we are increasing the y values or the outputs by 2, which will again give this a constant rate of change as we are adding 2 to each of the outputs, which will give us a slope or a linear function. But now compare that to example B in that table. As my x values are going up by 1, my y values are changing by different numbers. I can't say that they are each going up by the same number of adding them. What I would notice is that I would be multiplying by 2 each time. So this is obviously not a common difference, but we could say that these are a common constant factor. They are being multiplied by the same number, that number 2. This would be an exponential function. Now, you look at tables C and D, see what you think, whether they are linear or nonlinear, and then you can pause the video, and when you are ready to come back on, I will give a few seconds, and then I will continue on. So check these answers, and then come back on. So notice here, C, while the x values are going up by 4 each time, the y values are going down by 1, but they are going down by 1 through subtraction, so this would represent a linear function. In table D, as the x values are going up by 1, the y values are actually going down by a common factor of 1/2. Initially, we would obviously recognize that they are being divided by 2, but we always refer to our constant factor as multiplication. So times 1/2 is the same thing as dividing by 2. That would make table D an exponential function. When we are trying to evaluate exponential functions, it's very similar to what we would have done when we were doing our linear functions, in that we will take the value of x, which in this case is the number 3, and we are going to plug it in and solve for the y value. So when x is 3, all we have to do is replace the x into our equation and then use our order of operations, which will then say y is going to be negative 2 times 125. So y is negative 250. For the second one, when we plug in x is negative 2, remember what that is going to do for our expression. We actually have 1/2 to the negative 2 power, so we would really have 1/2 to the negative 2 power, remembering that the negative exponent is going to take the reciprocal of our base, and we change this into 3 times 2 to the positive 2nd power. 2 squared is 4, and then 3 times that is going to give us 12. So the value will be 12 when x's are negative 2. Then we can move on to C and D, and I'd like you to try those two. Again, I will pause the video for a moment for yourself to complete it, and then when I come back on, you will have the answers and we'll talk through those a bit. So focusing on letter C, remember the exponent to the 1/2 power is really the same thing as asking for the square root. So the square root of 9 is 3, and then 3 times 2 is 6. So the value of y when x's are 1/2 would be at 6. Moving on to letter D. When we plug in x to the 0 power, x to the 0 power is going to change our base of a 2 into 1, and then 1 times 1.5 would give us a value of y equaling 1.5. Next, we want to be able to graph one of these exponential functions. And as you can see, one of the ways to do this is to set up our table of values. And again, you can plug in any kind of values you would like to plug in. I would try to keep our numbers as close to 0 as we can to kind of keep the numbers smaller and more manageable. You would like to try to include a couple of negatives if possible so that you can see what is actually happening around the x and y axis. So as I plug my values in, again, I'm going to pause the video here so that you can have a few moments to figure out the table values with the range coming out for that domain of -2, -1, 0, 1, 2, and 3. And then we will come back on. We can just double check to make sure that we have the same ones. So hopefully you have the same values here. When I plug in the different numbers for our exponent, it's going to affect each of the outputs, obviously. When we have x's are -2, we get 1/4, -1 gives us 1/2, 0, 1, etc. going through the table. So step 2 is to plot the ordered pairs and connect with a smooth curve. Again, these should not be a straight line. This is a exponential function based on the common factor that we are seeing there of times 2. And so we will not get a straight line, and we want to connect it with a smooth curve when we are completed. So as I kind of plot some of these points, if I go to -2.25, I'm going to be somewhere in this range right here, -1.5, someplace in this range, 0, 1, 1, 2, 2, 4, and 3, 8. Okay? So when we plot these with a curve, and hopefully I can do the curve semi-smoothly, it will look something like this. And again, we know that these outputs and these inputs will be going on forever, so we want to put those arrows there. So then the question is, what is the domain and the range here? Well, the domain in this case is going to be all real numbers. We don't have any restrictions on this situation here. So we can write all real numbers. Our range, though, remember, our range are the things that we are seeing come out. In this case, if you think about what you are seeing in your table, remember a negative exponent is not going to make this output become negative. And if I'm taking a positive base and just doing the negative exponent over and over and over again, we are going to be approaching 0, but we're actually never going to make it to 0 for the y values. They will get closer and closer and closer, but never actually make it. So in this case, we are going to say y is going to be greater than 0. We will get y values, as you can see from the graph, that will be certainly greater than 0. We are not going to ever reach quite to 0 or anything below 0. Next we have one that's a little more involved than just the 2x by itself function. Now we have y equals 2 to the x power plus 3. So again, as you kind of go through your table, complete the table, and then we'll come back and we can see what you get for those, remembering to follow your order of operations once you plugged in your values. So now we want to graph the function y equals 2 to the x plus 3. So again, I'm going to pause the video so that you can complete the table of values with the domain of -2, -1, 0, 1, 2, and 3. And then when we come back, we'll discuss the range or the output from those, and then we will graph from there. So as you can see from the table of values, basically what has happened is our outputs in this situation have all increased by 3. So that plus 3 is actually going to help us kind of see how we're going to get a vertical translation here from our y equals 2 to the x graph. And again, by plugging in those points, you should hopefully be able to see that. And again, as I make my graph from here, what I'm going to be doing is I'm going to be looking at the different points we get, and it's hard to always get it exactly right, but somewhere around these points, 0, 4, 1, 5, 2, 7, and then 8, 9, 10, and 3 would be a little bit up in this range. Okay, and again, we always connect with a smooth curve. And now remember, we talked about how we are not going to really drop off completely all the way through here. And if you think about -3 power, the -4 power, the -5 power, etc., in this case, instead of getting to 0, we are actually going to start smoothing out towards 3. 3 is going to be kind of our bottom line that we will never go below. So if we were talking about the domain, and again we have all real numbers, and in this case our range is going to be now y's are going to be greater than 3. It'll never actually reach 3, and it certainly won't go below 3. Okay, again, we have another example here of another function, y equals 1/2 to the x power. Again, we want to make the table values, and we'll check back in a moment. So if you can complete that table of values, and then you can come back on and see how you did. So hopefully you got this table of values, and it kind of shows you how each of those become that. Notice when the 1/2 gets raised to that -2 power, again we do the reciprocal of the base to make it 2 to the +2 power, which is the 4, and then etc. through the rest of those. In this case, you'll notice that we are actually decreasing with our range as we go for the rest of these through. So now to plot these points, it's very similar to how we did that. So go ahead and plot those points, draw your curve, and we'll come back and check on that momentarily. So there's the graph of this function. I want you to notice a couple of things. Number one, I did use a scale on my y-axis of a 1/2 just to kind of stretch this out a little bit. They did use a scale of a 1 on the x-axis, so that hasn't changed, but I did use a scale of 1/2 just to kind of stretch it out a little bit so you could see it. But again, notice how it starts to curve off at that y equals 0 line, the x-axis, and it will never actually go below that. So again, when we talk about looking at our domain and our range, domain is going to be all real numbers, and the range, just like we did in that first example, is going to be y's are greater than 0, because we see y values that are greater than 0. We will never see them at 0 or below for this function. This last example, example C, this exponential function is a little more to it, and there's a little more things involved with it. I first want you to kind of look at making the table. So focus on the table first, and check back in to make sure the table is good, and then we can talk about the remaining parts of this, this slide. Now, these values might be a little more difficult to kind of come about, and I'm certainly happy to go through them with anybody, but we'll kind of talk through them a little bit, and hopefully you can see where those points came from. The first one, obviously, when I do the 1/4 to the -2 power, that flips over the base to make it 4 to the +2 power, which makes 16, and 16 times -2 is -32. When I plug in -1, again the reciprocal flips it over. This time it now becomes the number 4 times -2 is -8. This time when 0 goes in for my domain, it makes that 1/4 become 1. 1 times -2 is -2. When I plug in a 1, it becomes just 1/4 times -2, which becomes -1/2. 2 would make it 1/16 times -2, which is -1/8, and 1/4 to the third power is going to give you 1/64. 1/64 times -2 is -1/32. So those are my values, and they're going to be a little more difficult to plot. I'm going to pause the video to kind of get that on the screen, and we can talk about it from there. Now this graph is obviously not really neat, and it's very difficult to kind of draw when you get down to the 1/32 versus a -32. But basically what I did here, and it gives you the idea, I used a 2 scale on my y-axis, I used a 1 scale on my x-axis, and what it will happen is you will notice that it's now coming from the bottom on the negative side all the way up to the y equals 0 or x-axis line, but it never will actually reach 0 again. This time, though, it's approaching from beneath. So when I look at my domain and my range on this one, my domain is going to be all real numbers. And my range, this time, y's are going to be less than 0, because we don't see anything that's above 0 or at 0. Now, when I look at these two questions off to the lower left-hand side, what is the y-intercept? Well, we know the y-intercept is when x's are 0, and the y-intercept is the 0, -2. Now, where do I see this value in the equation? Well, I see this value right here, up top here, back in the function, that letter a. So we talked about how the exponential functions are y equals ab to the x power. This a value is going to be your y-intercept. And that's where we'll see that in all these exponential functions. So now we're going to start using the information that we know about the exponential function models to decide how we write an exponential function based on information that we are given. Here we have a graph of bacteria population y after x amount of days. So we want to write an exponential function that represents this. Well, we have the graph, and we certainly have some points here. We could very simply make a table of those points and come up with what we think is actually happening here. We have 0, 3, we have 1, 12, we have 2, 48, and you might already start to see the pattern that we are going to be focusing on. We definitely know that this is not a linear function because we are certainly not going by a common difference. What we will notice here is that as the x's are all increasing by the 1, we can notice here that these are increasing by times 4. So that's an important part of how we are going to start our function and how we're going to create the model for this exponential function. Okay, so now we go to the model, y equals a b to the x power. We just said in the previous example that the a is our y-intercept. Now in our y-intercept, obviously on the graph it kind of looks like it might be at 0, 0, but we were given the point at 0, 3. And it's because it's such a big giant scale that why it looks maybe on the graph, but we want to go and trust the numbers. So in our function, what we're going to be doing is we're going to say y equals 3. B is our common factor, and the factor that we are noticing change. So we are going to be saying 3 times 4 to the x power. And that is the function model for this bacteria population problem. Now with that, what we're going to do is we are going to then have one more question to answer and to find the population after 12 hours and also after 5 days. Well, 12 hours would obviously be 1/2 of a day, because we can see that we are dealing with days for our domains, so 12 hours would be 1/2 of a day. So the first part of this would say, and we'll give ourselves a little bit of room here, the first half would say we have our model, y equals 3 to the 4 to the 1/2 power. We know that to the 1/2 power is the same thing as 3 times 4, the square root of 4. So we would have 3 times 2, which would equal 6. And we know that that would be the population after 12 hours. Then when we switch over to the days of the 5th day, again for the model we would have 3 times 4 to the 5th power. When we evaluate the rest of this, 4 to the 5th power is 1024, and so y is going to equal 3072. So there you have it. Exponential functions obviously are much different than our linear functions. We are not looking for a common difference. We are looking for the common factors. The common factor is the b in the y equals ab to the x power. The a will be our y-intercept, and the x, which is where we are going to be plugging in our domain, will be the power of the function that will help us find the range values or the y. So we will be talking about some different types of exponential functions over the next couple of sections, but this is our general introduction, and hopefully everything seems pretty good.